All right, so I guess what I'm going to do, I'm going to go over this example with you again, just to make sure that you understand that, because we in class this one we had a few trial and errors until we finally picked the right u. So let me just go ahead and do that. So we tried a bunch of different things for u. We tried sine squared of 3x. We tried the cosine of 3x. We tried just 3x, and none of those resulted in us canceling out all of our x values after selecting those as our u. But the one that did end up working, or the one that I can already anticipate knows will work, will be if we chose u as just the sine of 3x alone. All right. So again, it's okay if you try out different u's, but then none of them work, and I think this is our fourth one that we're trying, and it's going to happen. But anyway, so we're going to go ahead and take the derivative of this. This is going to be, so the derivative of sine of 3x is cosine of the inside times the derivative of the inside, and then of course we have times dx. So when I go ahead and work that out, I try to get dx by itself, I know that dx is equal to du divided by 3 cosine of 3x. Okay, so now I go ahead and I do all of my substitutions. So I have the integral of sine squared of 3x is going to be just u squared, right? Because if u was sine of 3x, this is going to be u squared times cosine of 3x times, and then all of this becomes du divided by 3 cosine of 3x. All right. So, this is going to be nice because the cosines cancel. I have a 1/3, and remember, when we have a constant, we can move that in front of our integral. So now I'm going to have the integral of u squared du. So I'm going to go ahead and take the integral of just that. So that's going to be 1/3 times u cubed over 3 plus c. And then, of course, this turns into u cubed over 3 times 3 is 9, plus c, and then we can substitute back our u into this. And again, if it's cubed, make sure that for a trig function, make sure that the cubed is right there next, right after the letters of the trig function. So it's going to be sine cubed of 3x all divided by 9 plus c. Sometimes the answer choice will, if this is a multiple choice, it would say 1/9 sine cubed of 3x plus c, and that's the same thing. So that's that. Just wanted to quickly review that one because I would say that was one of the more challenging problems we did from our first class. So now we have this one. And a lot of times what happens is, so far when you see like all of the previous examples, I don't have these ones worked out. A lot of the times the u that we ended up choosing was inside of some kind of parentheses or some kind of radical, and that's usually a good u to try. This was one of the weird ones where it's not necessarily the thing that was inside of the parentheses. You just kind of have to recognize that this is almost like saying sine of 3x, right? Squared, and what we chose, really in a way, this is kind of like we chose what was inside of the parentheses as our u. That's always a good place to start. Another good place to start is a lot of times whatever expression is inside of the exponent is what you're going to end up choosing as your u. And I even say that over here. Like in your in the initial directions, it says, look for a piece of the function whose derivative is blah, blah, blah. If you're not sure what to use, try the denominator or something being raised to a power in the function. So a lot of times you're not even sure what to set as your u. I'm not going to give a percentage or something like maybe 70% of the time, 60%, whatever. If there is an exponent involved, a lot of times what's inside of the exponent is what you end up choosing as your u, and you'll see right here. So if I go ahead and I select my u as the exponent, it'll be 3x plus 1. So then du is equal to 3 dx. Okay, and then I'm just going to write it over here. I have dx is equal to, divide both sides by 3, du divided by 3. All right. Now I go ahead and I do all of my substitutions into this. So I'm going to go ahead and substitute everything. I have e to the u power, because we said that 3x plus 1 was our u. times dx was du over 3. And now I just go ahead and make this look nicer. I'm going to take the 1/3 outside, integral of e to the u du. Hopefully you remember that the integral of e to the u is just going to be e to the u again, right? So it'll be, let's see, our answer is going to be 1/3 e to the u plus c. Substitute back in our u from before. So it'll be 1/3 e to the 3x plus 1 plus c. And there you go. That's your final answer. Okay. All right, it's going to work the same thing over here. I have 5x e to the negative x squared. And again, kind of like what I was saying from before, a lot of times your u is going to be the exponent. The other good indicator is that if, like, quickly do the derivative in your head. If I did the derivative of negative x squared, that's going to give me negative 2x, which is pretty much the same power as the other part of the function, except the difference would be negative 2 versus 5. So that's what we'll do. We have u is equal to negative x squared du would be equal to negative 2x dx, right? I'll get dx by itself over here on this side. I have dx is equal to du over negative 2, right? So now I'm going to do now that I did all this work over here, I'm going to do all of my substitutions back into the original. So I have the integral of 5x e, and then a negative x squared is now our u, times dx, right? But dx now is du over negative 2, right? So if I clean this up, oh, shoot, no. It's du over 2x. My bad. Whoops. So yeah, it'll be du over negative 2x, and then the x's will cancel. Okay, so then now what we have here is we have 5 over negative 2, which we can take outside of the integral, so negative 5 over 2, okay, times the integral of e to the u du. Yeah, hopefully that didn't screw you up. But anyway, so yeah, and now we just go ahead and we have negative 5 halves. Integral of e to the u is e to the u. Because again, and the other thing too is think about what the derivative of e to the x is. It would be e to the x times 1, right? So then this will be plus c, and then of course we substitute our x terms back in, so it'll be negative 5 halves e to the negative x squared plus c. Okay. Yeah, so let's keep going. All right. So this one, again, and a lot of times what you have as your denominator would be the u, but in this case, this is just another scenario where the exponent is going to end up working. And you probably are looking like, well, if I took the derivative of the exponent, is that actually going to cancel out with something else? Just try it and you'll see for yourself. And, hopefully you are good. Hopefully there comes a point where you can see 1 over x and recognize that derivative will be, something with an x squared on the bottom. But anyways, we'll just go ahead and set our exponent. U is equal to 1 over x, right? And I'm going to write that out a little bit more, or rewrite this so that I can easily take the derivative. That's the same thing as x to the negative 1. So then our du is equal to, bring the negative 1 to the front, negative x, subtract 1 from the exponent, and then dx, which is the same thing as negative 1 over x squared dx, right? So now if I go ahead and get dx by itself, I can multiply both sides by negative x squared. So dx is equal to negative x squared du. Okay, good. I got dx by itself. I'm going to do all of my substitutions back into the original. So I have the integral of e to the u divided by x squared times, and now dx is negative x squared du. Do all of my x terms cancel? Yep, I have x squared and x squared that cancel out. I have a negative that I can move out to the front, so that's the negative integral of e to the u du. And by now you're probably tired of seeing this one because it's so easy now. So that becomes negative e to the u plus c. Bring back my u into my function, so that'll be our expression, negative e to the 1 over x plus c. There you go. All right. All right, let's do this one. So now, again, we have our exponent is now cosine of x, and you should be quickly doing the derivative in your head. The derivative of cosine is sine, so yeah, it will end up canceling with that. So let's just do it. We have u is equal to cosine of x, du is equal to negative sine of x dx. I get dx by itself, so dx is equal to du divided by negative sine of x. Right, now that I got dx by itself, I'm going to do all my substitutions back into this, and hopefully all the x's cancel. So I have the integral of sine of x e to the now u times dx is now du over negative sine of x. Sine of x is cancel. I have a negative that I can move out to the front, so negative integral of e to the u du. This is actually the same thing as that one over there. So it'll be negative e to the u plus c. Bring back my u as cosine. Negative e to the cosine of x plus c. Okay. So far, nice and easy. Now let's do this one. So over here, we can also apply this technique to logarithmic forms. All right. So like I said, a lot of times you can choose your exponents, right, as your u. A lot of times you can see whatever's inside of the parentheses as your u, right? And in a lot of cases too, what you'll notice, and this will actually be very helpful for like the future chapter, you can set your denominator as your u, okay? And you can quickly see that just quickly do it in your head. If I took the derivative of this denominator, it'll actually equal, or at least be the same power as the one up top. So that's honestly really the best place to start. So let's see, we have u is equal to 3x squared minus 2x. And then I have du is equal to 6x minus 2, and then all of this times dx, right? So then if I want to get dx by itself, I have dx is equal to du divided by 6x minus 2. All right, now I'm going to go ahead and substitute everything back into the original. It's the same process. So pick your u, take the derivative, get dx by itself, substitute everything, then integrate, then so on and so forth. So I'm going to go ahead and rewrite my integral. So this is the integral of 6x minus 2 divided by, now we said that this was u, times dx is going to be du divided by 6x minus 2. And this was a perfect cancellation. 6x minus 2 cancels out. And then I have the integral of 1 over u du. And hopefully, after all that integration practice from the previous section, you'll remember that the integral of 1 over u is the natural log of the absolute value of u plus c. All right. And then now I'm just going to go ahead and put my u back in there. So this is equal to the natural log of 3x squared minus 2x, and then all of that plus c. All right, and I'm going to remember, don't forget to put the absolute value there. And that makes sense, doesn't it? Because hopefully you remember that if I took the derivative, right, remember that derivative of natural log of 3x squared minus 2x? The derivative is just going to be the derivative of the inside, 6x minus 2, divided by whatever's on the inside. Okay, so, it is helpful to see what the derivative of all of this stuff is. So anyways, so again, we're going to, just like the whole purpose of this part is to see, okay, well, over here, I know that if I took my denominator, I just quickly did a derivative in my head. Derivative of tangent is secant squared. So that's, so the derivative of that would equal something else in the function. So that's what I'm going to set as my u. So I have u is equal to tangent of x. Du is equal to secant squared of x dx, right? So then if I got dx by itself, I have dx is equal to du divided by secant squared of x, right? Quickly do my substitutions back in there. I have the integral of secant squared of x over, now the bottom was now u times du over secant squared of x. Those cancel. Integral of 1 over u du, and now you pretty much hopefully you understand the process. Integral of 1 over u is in fact the natural log of absolute value of u plus c. And then I can plug this back in there and I get natural log of tangent of x plus c. Right? And remember, the purpose of having an absolute value with the natural log is that we want to ensure that no matter what x value we get in this, the inside does not become negative, because we cannot take the natural log of a negative number. All right, so now time for probably the most difficult version of u substitution with for integration. So let me remember what was typed here. So here's a slightly different type of integration. Although we will still utilize a substitution, we will go about it a little bit differently. Some textbooks refer to this method as a change of variable method. So yeah, this one is going to be one of those situations how, like, every time we've been doing u substitution, notice how everything cancels out nicely. This is one of those situations where it won't. And you have to do one extra little step in order to get that to work out nicely for you. You'll see. So instinctually, if I have something like this, I'm going to go ahead and set my inside as my derivative, which is confusing, because I mean, some people in class already pointed it out that if I took the derivative of this, I have a 2, which won't cancel out with that x on the outside. But you'll see. So let's just kind of go along with it. We have u is equal to 2x minus 1. du is equal to 2 dx, right? I can get dx by itself by doing du divided by 2, okay? And let's go ahead and do our substitution. So then we have the integral of x times the square root of 2x minus 1 is now u times du over 2. So you see a problem here. We have a term on the outside that still does not cancel. So one of the things that and it's really hard to tell what to do in this step or try to give you guys like, hey, here's every time you see this, this will work. Not necessarily, but whenever you see just a single x or just an expression that is only missing one x, right? Or an expression that only has just like an x left over on the outside or something, an x raised to the power of 1. In my mind, I always look back at this and I say, okay, well, I know that u is equal to 2x minus 1. At the end of the day, I want to make sure that I don't have any single x terms left on the outside. But if I look at this original u, it's actually kind of easy to get x by itself in that in this expression or in this equation, right? Because if I wanted to get x by itself, right? Let me go ahead and do this on a separate sheet of paper. I have u is equal to 2x minus 1. To get x by itself, this is just like basic algebra 1. I move 1 to the other side, add 1, add 1. I have u plus 1, my pen is dying, is equal to 2x. And then to get x by itself, I divide both sides by 2, right? And that's that. I have u plus 1 over 2 is equal to x. So let me write that over here. I have x is equal to u plus 1 over 2. Now that I kind of have this by itself, I can substitute this in place of x now, right? And it'll work out nicely. So then I'm going to have the integral, right, of now that I know that x is u plus 1 over 2, well, if I do that substitution, isn't everything now in terms of u now? I don't know why I'm expecting a response. This is a video of me recording myself in my living room. But anyways, but yeah. So then you can go ahead and let's multiply all this out. So this becomes the integral of, let me put u plus 1. This is multiplied to the top. du is over here. All divided by 2. The 2's on the bottom is 4, right? So now I can take out the 1/4 times the integral of u plus 1. And I'm gonna go ahead and I already know, like I'm anticipating that this is going to be u to the 1/2 power, right, times du. All right, so I can take the integral of this now. This is good. This is a simple enough integral for me to take. So I know, so that's the whole point of u substitution, is to rewrite all of your integration into something that's easy to integrate and then plug it back in terms of x, right? So with this one, if I were to, hopefully, you probably should pause the video and try it yourself, but hopefully you've done that. And now you know that in order to integrate this, I can get this term and distribute it to both of those on the inside. So then I have, this turns into the integral, 1/4 integral of, let's see, u to the first power times u to the 1/2. The exponents added together will be u to the 3/2. And then plus 1 times that is plus u to the 1/2 du. All right, now this is just a basic power rule integration. So this is going to be 1/4 times, and then I have u to the 3/2. So 3/2 plus 1 is u to the 5/2. And then I'm going to multiply that, or not, divide it by 5/2, the same as saying like multiplying by 2/5, right? Plus, and then u 1/2 plus 1 is u to the 3/2. And then dividing by 3/2 is like multiplying this by 2/3, right? And I'll go ahead and just distribute the 1/4. So this will be, I'll do every little step so that you can see. I mean, hopefully you recognize that 2/4 makes this into 1/2, but whatever. I won't skip steps. So 2u to the 5/2 over 10, because 1/4 times all that, 1 times 2, 4 times 5 is 20, not 10. And then this will be plus 2/3 times 1/4 is 2u to the 3/2 over 12 plus c. All right? And this becomes 2 parentheses. Now we can substitute our u back in here. U was 2x minus 1. So 2x minus 1 to the 5/2 power. Oh, wait, I can simplify this. 2/20 is 1/10 plus, and then our u is 2x minus 1 to the 3/2. 2/12 is 1/6 plus c. That's as complicated as u substitution will get. It's actually not that bad. You just got to remember that sometimes you might have to manipulate your u equation to get x by itself and then substitute that back in for the remaining x that's left to cancel out. So again, I recommend you pause the video and try this one on your own. But I'll just assume you did that already. But anyways, so now we'll go ahead and I'll think about this one. So with this one, a lot of times, like I said, what's in the denominator is what I said is my u, and in a lot of cases, what's inside of a radical or parentheses is what we said is our u as well. So why don't I just set x plus 4 as my u? All right. So then du is equal to just dx. So there's no need to get dx by itself. So now I can go ahead and I can substitute everything. I have the integral of, so 2x plus 1 over, let's see, that's going to be the square root of u times dx is just du, right? So now I look at this and I say, okay, well, all I have is an x term that needs to be canceled out. I think I can look at my u equation to get x by itself easily. So not only will I work with these two, but I'll just say that x is equal to, if I subtract 4 from both sides, it's u minus 4, right? So now I can go ahead and get this u minus 4 and plug it directly into that x there. So then this becomes the integral of 2 parentheses u minus 4 plus 1, all divided by, and you know what? Let me just, I know if I'm going to do integration, I don't know how to integrate a radical, but I do know how to integrate a 1/2 power. So times du. And let's make this easier to work with. I'll do every little step just to make sure that, no one gets lost here. So this becomes 2u minus, this will be minus 8, but minus 8 plus 1 is minus 7, all over u to the 1/2 du. And again, hopefully, I don't know how many times I'm going to repeat it throughout the year, but if I have multiple terms on the top and only one term on the bottom, hopefully that's the sign that you just break up your fraction and divide each term on the top by the one on the bottom. So this will be the integral of, so let's see, 2 divided by 1 is 2. U to the 1, so 1 minus 1/2 is u to the 1/2. And then negative 7 over u to the 1/2 is like saying negative 7 u to the negative 1/2 power du. Okay. And let's keep going. So then the integral of this, so this will be, I'm going to keep my constant, and then u to the 1/2 raised to the power of 1 or no, add 1 to the exponent, so u to the 3/2. And then divided by 3/2 is like multiplying by 2 over 3. And then this becomes minus 7. And then negative 1/2 plus 1 is u to the positive 1/2. Divided by 1/2 is multiplying by 2. And then plus c. All right. So let's clean this up. So I know if I combine my numbers here, 2 times 2 is 4. I'm going to substitute my u back in. So u was x plus 4. So 4 parentheses x plus 4 to the 3/2 power divided by 3. Then over here, 2 times 7 gives us minus 14 parentheses. U was x plus 4. And then that's to the power of 1/2. And there's really nothing else to do there. So plus c. And there we go. Look at us. Look at us doing some super advanced integration. Calculus is fun. You look at all that work and you're just kind of like, man, I am one hell of a student. Anyways, yeah, show this to your mom, and I'm sure she would be like confused out of her mind. Or anyone. All right. Anyway, I'm going to shut up. I'm being stupid. So you have, there are 2 ways you can approach these problems. Watch carefully. So, yeah, I guess I'll show you both ways. So first of all, now we've been doing a whole bunch of u substitution, but now we have u substitution with bounds. Oh no. So, what do we do with the bounds? Hopefully you remember that whenever we integrate, we plug the upper bound then into our function, then subtract that by plugging in the lower bound, and so on and so on. But with u substitution, it's going to be a little bit differently. Okay? So, one thing I can do, well, first of all, let's pretend those bounds don't exist, and let's do this u substitution like we normally would. So I'm looking at this, a u substitution. I'm like, I think I can set this inside the parentheses x squared plus 1, because I take the derivative of that. That'll be 2x, and that x will cancel out. Perfect. So I'm going to go ahead and set u as what's inside. So I have x squared plus 1. du is equal to 2x dx. I get dx by itself. dx is equal to du divided by 2x. All right. So now we have all of this, and we can go ahead and do all of our substitutions back. So we have I'm not gonna put my bounds in, and you'll see why. So I have x parentheses x squared plus 1 is u cubed times dx is, now we know dx is now du over 2x. X is cancel. So now this becomes the integral of, I have a 1/2 that I can take outside the integral. So I'm going to put 1/2 there. Integral of u cubed du. All right. So now we have this situation. So now you're probably wondering, what about those bounds? Let's put 0 and 1. Here's the thing. The 0 and 1 bound, okay, that is only relevant for x terms. Our bounds are 0 and 1 when everything is in terms of x. But we have everything in terms of u. We should probably change our bounds. So I'm going to write over here next to our substitution area our new bounds. Okay. So I'm gonna put, so when I had x is equal to 0 and I have x is equal to 1, what is the corresponding u bounds for these two values? Well, don't you know that u is equal to x squared plus 1? So for x equals 0, if I plug in 0 into this, my u bound is actually going to be 0 squared plus 1, which is just 1. My u bound for this one is going to be 1 squared plus 1, which is 2. So these are the bounds that I'm going to use for my integral. So from 1 to 2. Okay? So make sure that whenever you do u substitution and there are bounds involved, you have to change your bounds. I've tutored this subject for so long, and this is the one thing that students are always forgetful about. All right? So don't be forgetful. Change your bounds when you see bounds. So now I'm going to go ahead and do this u substitution. So now I have 1/2 of times u to the 4th over 4, right? And then that's the integral of that. So let me write that instead as u to the 4th over 8, right? And now I have to do this from my bounds, from the bounds of 1 to 2. So I plug in my 2. So 2 to to the 4th over 8 minus 1 to the 4th over 8. So that becomes 2 times 2, 16. 16 minus 1, 16 over 8 minus 1 over 8 becomes 15 over 8. There's my answer. Okay. I'll quickly do this one. God, this is getting to 30 minutes. Okay, let's just do it quickly. So now I have my u is equal to 2x minus 1. du is equal to 2 times dx. And I can get dx by itself. Dx is equal to du over 2. All right, so I'm going to go ahead and plug this back in. So now, oh, and you know what? While I'm at it, I'm going to make my new bounds. Let's not forget that. Okay, I'm going to make my new bounds. So I know that for x equals 1, my u is in fact equal to 2 times 1 is 2 minus 1 is 1. Oh, that actually worked out nicely. Same lower bound. And then for x equals 5, my u, 5 times 2 is 10. 10 minus 1 is 9. So those are going to be my new bounds. Not from 1 to 5, but instead from 1 to 9. So I'm going to do my substitutions. I have, let's see, I have the integral from 1 to 9. And then I have x over the square root of u times du. Well, dx is now du divided by 2. Oh, crap. My x's don't cancel. Can I manipulate my u to get x by itself nicely? Yes. I haven't done this problem in class, so I forgot what, I wasn't able to quickly anticipate. But in order to get u by itself here, I got to add 1 divided by 2. So I know that u plus 1 over 2 is equal to x. So that's what I'll substitute back into this. Ugh, this is going to get ugly. No, it's not that bad. So then this will become the integral of, let's see. If I separate my x, I'm going to separate my x out over here and treat this as like 1 over u to the 1/2 power, just rewriting everything. So times x, which we know is u plus 1 over 2 times du over 2. All right. So let's kind of combine everything. So I have integral from 1 to 9 of u plus 1 over 4u to the 1/2 du. I'm going to take the 1/4 out. Right? I'm just trying to clean this up to make it easier to do the integral of u plus 1 over u to the 1/2 du. And now I'll go ahead and separate this out, divide out my terms. So u over 1/2 will be, so 1/4 integral of, so 1 minus 1/2 is u to the positive 1/2. This becomes plus u to the negative 1/2 du. This looks like the integral we did before. So that becomes 1/4 u to the 1/2 plus 1, so, or 1/2 plus 1 is u to the 3/2, divided by 3/2 is like multiplying by 2 over 3, plus add 1 to this exponent, it's u to the positive 1/2, divided by 1/2 is like multiplying by 2, right? From 1 to 9. Okay. Man, this is going to be quite a amount of work. So then I want to distribute my 4 in now. So if I distribute my 4, 1/4 times 2/3, the 2 and 4 will cancel out, and that'll be like, or it'll be like saying 2 over 12, which will be u to the 3/2 over 6, plus, and then the 2 times 1/4 will be like 1/2, so u to the 1/2 over 4, no, 2, right, from 1 to 9. Now let's go ahead and plug in, Now let's go ahead and plug in our upper and lower bounds. So if I plug in 9, that's like saying 9 to the 3/2 over 6 plus 9 to the 1/2 over 2. Then all of that minus, let's see, 1/6, because if 1 to any power is just going to be 1, plus 1/2. Okay, I should have given myself more space here. So 9 to the 3/2. First of all, I can take I can do 9 to the 1/2 first and then cube it, right? So 9 to the power of 1/2 would be the square root of 9, which is 3. 3 cubed is 27. So this will be like 27 over 6. And then 9 to the 1/2, that's like the square root of 9, plus 3 over 2 minus. And then I have 1/6 plus 1/2. Okay. So then I'm going to go ahead and combine like at least the fraction. So 27 over 6 minus 1 over 6, because if I distribute my negative to both, 27 minus 1 over 6 is like saying 26 over 6. And you know what? I'm going to go ahead and make sure that these denominators are all the same. So 3/2 is the same thing as saying, if I want this to be 6 on the bottom, multiply by 3 over 3 is like 9 over 6. This is the same thing as saying 3 over 6. So 9 over 6 minus 3 over 6 is minus or plus 6 over 6, which is equal to 32 over 6, which is equal to, oh my God, what's this divided by 2 is 16 over 3. There we go. I may have done that math wrong. Double check for me. Not sure. But anyways, I'll stop it there because this, I mean, we didn't even do this problem in class, but so you got a head start. But anyways, yeah, hopefully this was helpful. We'll do these 2 examples when we get to class on Monday, and then that's going to be it. Take care.